So, welcome back to one more lecture on introduction to soft matter, and today what we are going to see. So, last class we were discussing polymers, right. So, we will just quickly review a couple of important points that we were discussing, and so we are looking at polymers, and some of the important points or the issues that we discussed is that polymers basically consist of long molecular chains of covalently bonded atoms. And essentially the idea is that there is some structural unit, there is a unit of a polymer, let us just call it A for the time being, and this A is going to covalently bond with another A, and it is going to keep on going on, and this becomes a polymer. Now, in a situation like this where a structural unit, so this is a structural unit, it is bonded to only two other structural units, and that is repeated again and again. This is known as a linear polymer. Whereas, so this is a linear arrangement, okay, of units, and hence called linear macromolecule or linear polymer. Now, the linear word does not mean that the chain is in reality, that is how the polymer really looks, like a straight line, that is what not, it does not mean that. But of course, when we say linear, then it means that some other form is probably also possible, that is why we have to give a special name to this, and that is true because you can have what is called as a branched arrangement, where you have an A and then you can have another sequence of, here I am running out of space, so I am just going to so this is a branched arrangement, okay. So this is a branched macromolecules. Okay. Another important point that we discussed last time was that one of the simplest polymers is polyethylene. And here your CH2 is the monomer, is the repeating unit. And it is basically made using ethylene and through the polymerization of ethylene, and this polymerizes and this becomes a repeating chain that just continues for some n, where this n is a very large number, large integer, and this is how the polyethylene molecule is formed. This also brings us to another class of polymers made from this molecule, where I have taken one H out and instead I am going to replace it with an X, where this X is some other group, some other chemical group. So, a class of polymers made from this is known as vinyl compounds, or vinyl polymers are called vinyl polymers. So, what can X be? For example, your X can be different groups. It can be, for example, a CH3 group. It can even be part of a benzene ring with one hydrogen removed. So, you can have these different vinyl groups possible. So, maybe we should look at some examples of common polymers. Okay. So, what I will do is I will create a section. Okay. So, for name of the polymer, then here we will put the monomer, and this is what the structure of the polymer looks like. So, let us say, so we obviously started with polyethylene. So, let us just populate it with that polyethylene. The monomer was CH2CH2, and here you have so how about, so another one is called polystyrene. So, another famous polymer. In this case, your X takes on, becomes a benzene ring. So, instead of one H, we have now a benzene ring. So, when this polymerizes, you have so I am just missing a 2 here. H. Another one is called polyacrylamide. And here your X takes on the value CONH2. So, this is CONH2, and you have the structure looks like the following. Another example is polyvinyl chloride, where we take the X as a chlorine atom. So, this is called polyvinyl chloride, and in this case here X is a chlorine atom. So, this is obviously it is just going to be this form. Then you have polyisobutylene, where both the hydrogen atoms are taken out in this case and are replaced by CH3. So, obviously, you know how to draw the structural unit for this. We will now have a CH3, 2 CH3 units. Line here, and this is polyisopropene, and here your chain slightly more complicated. So, you have a CH2, then you have a CH, you have a CH3 here, but this carbon is now attached to CH2. So, if you had to polymerize this, then you will take this particular bond here, the 2 double bonds, and use that to cause polymerization. So, your polymerization should look like CH3. These are some of the examples, the common examples of the polymers. So, if you are working with a polymer in the lab, it is just good to know what is the chemical formula for this, and that will help you in evaluating many of the important properties. Now, just quickly going back to that point that a polymer is basically made up of structural units. So, let us just say that there are these structural units A, which are repeating again and again, right. So, at some point this chain has to end, right, and when the chain ends, then it might not always end in the same structural unit. So, here you might have, so I have already used X for something else, so maybe I will use the symbol Y. So, it ends in Y, which is a special unit, and this is also called the end group. Okay. So, these end groups are usually different than the repeating unit. So, this is your end group. So, polymers where chains terminate, special groups can be found, and these end groups can be very important in also determining, let us say, the overall charge and other properties of the polymer molecule. So, we can already see that there is quite a bit of complication, right. So, you have the polymer molecule, the macromolecule, but it is not just sufficient to know which monomer it is, because the monomer is obviously going to be there, but how is the monomer causing the or participating in the polymerization, that is important. So, you have to know the formula, but at the same time you also have to understand how whether it is a linear molecule or is it branched, and then what end group does it have. So, till now, but this example is basically relating to a polymer which is just made up of one structure unit which is repeating again and again, right. But then there are many polymers which are not composed of just one structural unit, it can be composed of many different structural units which can also go on repeating. So, many synthetic polymers are built from multiple structural groups, structural units. These are known as copolymers. So, in contrast, a polymer like this, which is made of only one structural unit, this is known as a homopolymer. Okay. So, this is an example of homopolymer. So, all the examples that we just did, these are all homopolymers. Okay. So, maybe you will just make a note. These are homopolymers. In a copolymer, you can have a situation where you have, for example, two structural units, maybe let us just call them A and B. So, if you have that, you can have a situation where you have A repeating, and then you have another and then after some time again. So, copolymers can also be of different types, random copolymer, etc., grafted copolymers. We are not going to discuss too much about that. That also takes us into the chemistry of how we should be making these polymers. That is outside of the scope of this particular course, but it is useful to know that these exist and you might need them, and if you need them, then you have to look into the specifics of how they are made. Now, the typical synthetic polymer Okay. So, the typical synthetic polymer, a polymer which is made through an industrial process, can have many different molecules or structural units together. So, typical synthetic polymer molecules can have molecular weights between, let us say, 10,000 to easily a million or even more at times grams per mole. This is just an example value, and a tobacco mosaic virus, for example, is of the order of 10 to the power 7 grams per mole. So, these large molecules can have a lot of very high molecular weight. Just contrast it with a simple molecule, let us say oxygen. Right? Oxygen's molecular weight is about 32 approximately, 32 grams per mole is what it weighs. But for a polymer it can be 10,000 or even 1 million. So, that gives you a contrast as to how big the polymer molecules are in contrast to some of those simple molecules. Right. Now, when you are making these polymers in an industrial process, there is no reason, or it depends on how the polymer is going to be manufactured, that you might end up with a set of polymers which are not the same molecular weight. You can also have a process of fabrication in which perhaps all the polymers are going to have the same number of repeating units, and in that case you would call it a monodisperse polymer, because all the polymer molecules have the same n in that sense. So, the number of times the mer is repeated, but usually you would not get that. Okay. So, in any in any manufacturing process, you are not likely to get a set of molecules which have the same molecular weight. So, we quickly discuss these two terms. So, monodisperse is another important term. Monodisperse is when all polymers molecules, all polymer molecules in a sample have the same molecular weight. So, obviously, the contrasting word would be polydisperse, but most industrially sourced polymers are polydisperse. So, the moment you have a dispersion, then you must have some way of calculating an average molecular weight, because now you have a whole set of molecular weights that is there in your solution, right. So, for polydisperse samples, so for polydisperse samples, we can define a number average molecular weight. So, let us say we define this quantity Mn, which is an average quantity, and that is given as a summation of, I am going to divide this, that is why it is going to become average, Ni. Okay. Ni is the number of moles of the ith component. And on the top you can probably guess that you would have an Mi, which will stand for, in this case both of them are being, these summations are being done over I, and this M is the molecular weight of the ith component. So, some people argue that this is not always a very good measure, because it biases the sample if the sample has molecular weights or sample or components which have very low molecular weight versus and or very high molecular weight. So, then this M average can vary a lot. So, then the other suggested average is what is called as a weight average molecular weight, in which case we define this as, and weight is a slightly misleading term, it is supposed should be mass. Okay. So, if you want to understand it in terms of that. So, let us say you have Mi Ni, okay, and Mi Ni are the same as we discussed before. This is summation sign. On the top you have again Mi Ni, which is in a some measure of mass of the ith component, and that is multiplied again by the number of moles of that. Number average molecular weight and this other one is usually called the weight average molecular weight. Okay. And this ratio of the two averages is usually taken as a very another, it becomes another important number. So, this ratio MW by Mn average, this is, it represents certain heterogeneity in the sample, it is a heterogeneity index. And is usually taken as a measure of polydispersity. So, obviously, if you had a sample where there is only one molecule present with one molecular weight, then your this ratio would just be 1, right, and the more it deviates from 1, it means that the sample has more and more molecules of different molecular weights. So, this is sometimes also called the polydispersity index or PDI. So, it is also called polydispersity index or PDI. Okay. So, in a normal situation you might have a very large distribution. So, sometimes when we source these polymers from an industrial location or an industrial source, what we end up getting is not a set of molecular distributions, but entire curve of molecular distributions. So, let us say this axis is molecular weight, and on this you have the amount of polymer. Right. So, then this average quantity that you had just discussed, which was initially we were writing it as a summation. So, in this case the summation is obviously not going to work, right. So, instead we are going to replace this n with a dn, and then you have to put the limits for that, and then it is the summation of n dn. Another quantity that people often encounter is called the degree of polymerization. So, how do you calculate the degree of the polymerization for a given polymer? You take the molecular weight of the entire polymer. Okay. So, this is m of the polymer, and you divide it by the molecular weight of the monomer, right. So, this is the molecular weight of the entire polymer molecule, and this is molecular weight of monomer. Right. So, as the degree of polymerization changes, then your property should change. Right. So, going back to the degree of polymerization. So, let us take polyethylene. Okay. Polyethylene or ethylene, the monomer itself at normal room temperature is a gas, but then as you keep on polymerizing it, the polymer would become liquid at normal room temperature and pressure, and if you keep on doing it, if you increase the degree of polarization to even higher numbers, then at some point this natural state, when we say natural state means the state of the material at room temperature and pressure, will become that of a solid body, right. So, maybe so from literature we know that. So, let us just call this dP, yeah, degree of polymerization. So, I will just quickly draw. So, this is let us say degree of polymerization dP, here is your molecular weight, and then this is character. Now, from literature, and this is some data that I have taken from the book of Brinson and Brinson. So, first of course, if you have a dP of 1, then you are dealing with polyethylene itself, the molecular weight is 28, and here you have a gas. If you have a molecular weight of 6, then you will end up with 170, and in this case it becomes a liquid. See, it is not a simple multiple of 28, by the way, because you have the end of the molecule to take care of. Right. So, and if you have 35, then your molecular weight, again it depends on the particular system that you are dealing with, you will end up with a grease. So, that is why this polymerization is very important, and how much is the molecular weight, these numbers are very important when you are working with any of these polymeric when any of these compounds. Now, there is also one more molecular weight, which is viscosity average molecular weight. So, I will just mention it here. So, this is called viscosity So, sometimes you will find that manufacturers will report the polydispersity index. Whenever they report an average molecular weight, you must ask yourself, or you must ask the manufacturer, which particular average value are they reporting? Is it the number average, or is it the weight average, or is it the viscosity average? More often than not, it is weight average, but some cases they can also report viscosity average. The viscosity, the equation relevant to this, I will discuss at a slightly later stage, because I have to introduce a few other things with that in that case. What we saw today is, we take a quick review of that. We looked at some common polymers, polyethylene, polystyrene. We discussed what their structures look like. Then we discussed some of the terms that you encounter again and again in polymer literature, and copolymers, homopolymers, monodispersity, polydispersity. And then we looked at a couple of important quantifiers, which are the number average molecular weight and the weight average molecular weight, and the polydispersity index, and also the degree of polymerization. Okay. So, next class we will have a little bit more discussion on polymers. We will keep this going. Okay. So, we will stop here today.